Hello and welcome to this presentation. In this presentation I will talk about the robot assistant I'm working on that uses automated learning techniques to find good models for running experiments on a variety of tasks such that others can reproduce and improve on these experiments. This is how it works. OpenML provides a platform where scientists can post important data, inviting anyone to help analyze it. It structures and organizes all results online and allows you to search, compare, visualize, analyze, and download all combined results. Via an API, we can retrieve tasks that define what should be done on a particular dataset. An example would be supervised classification on the MNIST dataset of handwritten digits. This task specifies that we should do a tenfold cross-validation and gives a list of which data will be in the training set and which data will be in the test set for each fold. The task also tells us what results must be uploaded and what information is necessary to ensure that uploaded results are interpretable and verifiable. It is up to us to find a model that suits this task, execute it, and publish the results back to OpenML. And that is where the robot assistant comes in. The robot assistant uses a simple pre-processing pipeline to fill missing values and encode categorical values using a one-hot or one-of-a-case scheme. Via a workflow interface, it calls the automated machine learning algorithms to do their work and come up with the best results they can find within a given time span. After that, the robot assistant can start working on its task using the fitted workflow. The initialized workflow now behaves as a normal, untrained estimator following the scikit-learn API. So for each cross-validation step, it refits the pre-processing pipeline and retrains the model on the training set and predicts the result. The robot assistant then publishes these results and starts working on its next assignment. OpenML processes the results and should accept the parameters we tell it that we used. However, the API does not support all types of parameters yet, such as pipelines, but this will be fixed later. And then we should be able to reuse the workflow while skipping the model building step. Two automated machine learning algorithms are currently integrated, Tpot and AutoScaleLearn. The advantage of using these two is that they are both written in Python and both make use of the scikit-learn library. Tpot stands for Tree-Based Pipeline Optimization Tool and uses genetic programming to find an optimal pipeline with pre-processing and feature selection included. AutoScaleLearn, on the other hand, uses Bayesian optimization and complements this with meta-learning. They do so by selecting a specified amount of configurations to precede this Bayesian optimization process. Next to that, rather than just selecting the best model, AutoScaleLearn saves all models at the end. It constructs an ensemble through a greedy procedure that starts from an empty ensemble and then iteratively adds the model that maximizes ensemble validation performance with uniform weight, but allowing for repetition. While this should increase performance, it makes it necessary to refit all models on any new data. However, this kind of operation is very exhaustive on a tenfold cross-validation and it dramatically increases execution time. During a small benchmark, it also did not seem to improve performance under current circumstances. So I have set up AutoScaleLearn to only select the best algorithm. Putting everything together, we now have a bot that builds a model with Tpot and AutoScaleLearn and uploads this to OpenML. We can now let this bot run continuously and let it discover good models that others can reuse and improve on. It also provides a baseline of what the performance can be without complex feature engineering. And so, after we have run the bot for a few days, we can analyze some results. We can determine how well Tpot and AutoScaleLearn perform against each other, but also how they perform against the already existing runs on OpenML. I'm Joachim van Scholen. has executed over 300,000 runs with Weka machine learning algorithms on a vast variety of datasets. In this graph, you can see how well AutoScaleLearn and tpot perform relatively against the best Weka runs, on average. So the Weka runs have the advantage here, because only the single best Weka run is selected, while for tpot and AutoScaleLearn, we take the mean on all their runs for that task. The scores of AutoScaleLearn and tpot are normalized by the best Weka score. The y-axis on the left shows how close the model score to the best Weka score. A 1 means that the algorithm scored exactly the same as the best Weka run. Often one of the two automated machine learning algorithms score more than 99% of the best Weka run. To give a better visualization of the differences between AutoScaleLearn and tpot, I have made this graph. When AutoScaleLearn wins against tpot, you'll see a red bar on top, indicating how much better AutoScaleLearn performed. When on the other hand tpot wins, you will see a blue bar on top. An interesting observation seems to be that on average tpot wins more for more datasets, while the difference in score is higher when AutoScaleLearn wins. Overall, I think there's not much difference in score between AutoScaleLearn and tpot, and that they complement each other very well. And I hereby have come to the end of the video. I hope you have a nice day, and I'll catch you in the next one, or something.